Wave motion and types of waves. A wave travels along its medium, and by medium, here the medium is water. The wave travels along the medium, but the individual particles of the water just move up and down. All types of traveling waves transport energy. The study of a single wave pulse shows it has begun with the vibration and transmitted through internal forces in the medium, and this time the medium is this piece of string here. Continuous waves start with vibrations too. If the vibration is simple harmonic motion, then the wave will be sinusoidal. And what this picture is also showing you is the motion of each individual particle of the string, just like in the water. This particle, let's pick it right there. It's not going anywhere. Not going anywhere, and here it moves up, but then it's going to come back down. It does not move in this direction. It's just going up and down. There are some wave characteristics here that we have to know, and we've dealt with these in simple harmonic motion. They're the same thing. We have amplitude, which is the maximum displacement from a rest position. We have the wavelength, which is the distance between two peaks or between two troughs, like that. Frequency, how many waves per unit of time. Period, how long it takes before the wave repeats its motion. And finally, wave velocity. Wave velocity is the velocity at which wave crests, or any other part of the wave, moves. A wave crest travels a distance of one wavelength in one period, capital T. So the velocity, which is just delta x over delta t, is lambda over t. And frequency, of course, is 1 over the period. So the wave velocity is also the wavelength of the wave times its frequency. The velocity of a wave depends on the medium through which it is traveling. The velocity of a wave on a stretched string is related to the tension force in the string, and the mass per unit length of the string mu, also known as the linear mass density. So here's the formula. Velocity is the square root of tension over the linear mass density. The linear mass density is in kilograms per meter, and of course the tension force is in newtons. There are two types of waves, longitudinal and transverse. The motion of particles in a wave can either be parallel to the wave direction, so picture this as a slinky that you're pushing back and forth. So you compress it, then it expands, then it compresses again, and the distance between two compressions or two expansions is the wavelength. Then you can take that same slinky and move it up and down, vibrate it up and down. Now you have a transverse wave where the slinky itself, all the particles on the slinky are going up and down, but the direction of the wave is this way, so the disturbance is perpendicular to the motion. Sound waves are longitudinal waves. Here we have an expansion, and that happens when your speaker, see, it's pulling inward, it's pulsing inward, so you get these expanding places. Then, if you have the speaker pulse outward, you get a compression, and that's the dark lines here. Same over here. So the speaker pushes the air, that would be the compression. Then when the speaker cone comes back in the other direction, that's when you have an expansion. Light waves are transverse waves. So the light is going in this direction, but the electric field and the magnetic field that make up the light, the photons, is vibrating in that direction or coming out of the page and going into the page. So it's perpendicular to the motion, transverse wave. The energy transported by a wave is proportional to the square of the wave's amplitude. The intensity is defined as the power transported across a unit area perpendicular to the direction of energy flow. So the intensity is power over area, and since the surface area that you're going through, because it's going out in all directions like a sphere, is 4 pi r squared. Therefore, intensity is inversely proportional to the square of the distance from the source, and that's what we have over here. What is the velocity of a wave with a period of 3 seconds and a wavelength of 2.1 meters? We write down our givens, the period and the wavelength. we use the wave velocity formula, which is lambda over period, and substitute in the givens, and we get the velocity is 0.70 meters per second. Now, why did we put that other zero there? Well, we have two significant figures here, two here also, so our answer should have two significant figures. So this is precise to the hundredths place, 0.70. 7 and 0 are significant. This one is not a significant figure. What is the velocity of a wave with a frequency of 5 Hertz and a wavelength of 0.20 meters? Here's our givens listed up here so we know where we're going. Based on that, we will use the wave velocity formula, which is the velocity is lambda times frequency, substitute in our givens, do the math, and we get a velocity of 1.0 meters per second. What is the frequency of a wave with a wave velocity of 1.6 meters per second and a wavelength of 0.50 meters? The givens are up here. And we know to use the wave velocity formula, but first we have to solve for frequency because that's what we're looking to get. Don't just plug the givens in and do some division then. Do your algebra first. So we divide both sides by the wavelength, switch left to right, right to left, and we get the frequency is v over lambda. Now we can substitute in our givens, and we find that the frequency is 3.2 Hertz. What is the wavelength of a wave with a wave velocity of 2 meters per second and a period of 5 seconds? The givens, the velocity, and the period, wave velocity formula, but we need to solve for t, period. Always do the algebra first, plug the numbers in at the very end. So we multiply both sides by t, and we switch around the equation so that we have lambda is velocity times the period. Substitute in our givens. You can see how the seconds cancel out, and we get a wavelength of 10 meters. A string with a linear mass density of 80 grams per meter, and we've already converted that to kilograms per meter by moving the decimal place 3 places to the left, is under a tension of 20 newtons. What is the velocity of a wave on the string? We write down the givens. Right, here's a linear mass density, mu. Here's the tension force. And we use the velocity tension equation, which is velocity is the square root of tension over mu. We substitute in our givens, linear mass density, tension. Make sure you remember to take the square root. And we get a velocity of 15.8 meters per second. The wave velocity in a piano string of linear density 5 grams per meter, which once again is 0.0050 kilograms per meter, is 140 meters per second. What is the tension in the string? Here's our givens. So once again, we need the velocity tension equation, but we want to solve for tension. So as always, we do the algebra first. And when you ever have a square root, you kind of want to get rid of it. So how do you do that? Well, let's square both sides. So when you do that, you have velocity squared is equal to tension over linear mass density, right? We got rid of the square root by squaring it. Then we multiply both sides by mu, switch tension to the left side, and we get tension is v squared times mu. Substitute in our givens and make sure you remember the power of 2 there, and we get a tension of 98 newtons.